very good afternoon to everyone. We have gathered here to understand and advance our knowledge in the field of magnetic storage media. As Sir has mentioned in its first question that the first storage system we all work with is our brain, which stores many information for us, but if we do not recall or revise those information, we tend to forget it. That's why to get the maximum output of this course, let's have a revisit and recall to the fundamentals of magnetism through this lecture. So we'll start with the fundamental question, what is the origin of magnetism? Followed by the quantities and units which we use to quantify these magnetic behavior of the materials, followed by forms of magnetism, and finally ferrite crystal structures and their magnetic behavior. So magnetism is one of the fundamental questions or phenomena to be addressed in condensed matter physics. It was observed that magnetite attracts iron nails. This small observation led us to the broader concept of magnetism, which is an ability of a material to exert either an attractive or repulsive force without any physical contact. This attraction can be explained either in terms of magnetic induction or via magnetic field concept. When a magnet is brought near to a magnetic material, then it will induce opposite magnetic polarity on a material, and this way induction leads attraction. Also, we can explain it as magnetic poles create their own magnetic field, and this field exert force on the material which is placed nearby to it. To understand how magnetism originates, we must examine this phenomenon at microscopic level, where we understood that magnetism originates from the magnetic moment which arises due to the motion of electrons, specifically the orbital motion and the spin motion. So we can say that if we have an atom which has unpaired electrons, then it will possess a magnetic moment. Now here comes a question, if all the atoms have certain amount of magnetic moment and all the materials we have is made up of such atoms, then why all of them are not magnetic? Because in most of the materials, these atomic magnetic moment orient themselves in a way such that they cancels out each other effects and resulting no net magnetization when there is no applied field. However, we have certain materials in which due to spontaneous alignment of these atomic magnets, due to the exchange interaction, we get certain magnetization even in the absence of applied field. Thus, we can say that the magnetic behavior of a material is not merely decided by the presence of magnetic moments, but how these magnetic moments are arranged inside the material. Also, we can influence this alignment through an external magnetic field. With this, we comes to the end of first section, in which we discussed how magnetism originates, why all the materials are not magnetic, and we can influence this alignment through external magnetic field. Now let's have the second section of our discussion, which is system of units. We have two systems, SI and CGS system. Both of them describes the same physical reality but differ in the way this reality is visualized. First, let us consider the quantity magnetic poles. Historically, we see that magnet has two poles. The force which we feel assumes to be originated near the end of the magnet, which is defined as the poles. The force of attraction between these poles is directly proportional to the product of pole strength and inversely proportional to the square of distance between them. If in CGS system we measure force in dyne and distance in centimeters, then pole of unit strength will be 1, which exert a force of 1 dyne on another unit pole which is located at a distance of 1 centimeter. Next, this pole creates magnetic field in its surrounding, and this field exerts force on the other materials. The force which this field creates is directly proportional to the product of pole strength and the magnetic field. A field of unit strength.
You have to be very clear because maybe you will have examination towards that. So, you will note of the things.
So, the force this magnetic field will exert is directly proportional to the product of pole strength and the magnetic field intensity H. Therefore, a field of unit strength H can be defined as it exert a force of 1 dyne on a unit pole. The unit for magnetic field strength is 1 oersted. This magnetic field can also be explained in terms of lines of force which express both the magnitude and the direction of magnetic field strength, which is equal to the number of lines of force passing through unit area perpendicular to the field. In CGS system, if we have a field of strength 1 oersted, then this will correspond to a 1 line of force per centimeter square, which also equal to 1 Maxwell per square centimeter. For example, if we have a sphere of radius 1 centimeter and surface area 4 pi centimeter square, then the total lines of force will be 4 pi. Next we have magnetic moment, which is denoted by M and is defined as the torque experienced by a magnet when placed in a magnetic field of strength 1 at an angle 90 degree. For a bar magnet, the mathematical expression for it is a product of pole strength multiplied by length of the magnet. It's a vector quantity and is directed from south pole to north pole. If magnet has any other orientation in the magnetic field, then it will have potential energy which is equal to minus m dot h. From here, if we measure energy in erg and magnetic field intensity has unit oersted, then from here we get the unit for magnetic moment as erg per oersted, which is also equal to 1 EMU, which is electromagnetic unit. Next we have intensity of magnetization, which describes the degree to which a material is magnetized. It is the ratio of magnetic moment per unit volume and is denoted by capital M. Because the unit of magnetic moment is EMU, therefore the unit of intensity of magnetization is EMU per centimeter cube. Sometimes we need to compare magnetic behavior or magnetization at different temperature, then we will prefer using mass at the place of volume to avoid thermal expansion. And therefore we define a quantity specific magnetization denoted by sigma. It equals magnetization per unit density and has unit EMU per gram. Next we discuss the SI units, which has current in the picture. So we know that if we have a current loop, then it will create a magnetic field and behaves as a magnet. If such a current loop can be placed in a uniform field, then it will feel magnetic force and a torque will apply on it, which turns it and has magnetic moment. This magnetic moment, from the formula of magnetic moment, we get one more unit for magnetic moment in SI units, which is ampere centimeter square. Also, if we have a primary winding and current I is flowing in it, then it will produce a field of H oersted within the ring. The total number of lines of force is defined as magnetic flux, which is equals to H times A, where A is the area. If from this figure we cut out small section and if there is no magnetic material present, then there will be H lines per centimeter square due to the current I flowing in the primary winding. If we place a material inside this cavity, then due to this field, the material gets magnetized and we have additional 4 pi m lines per centimeter square strength of magnetic field, which is due to the magnetization of the material. Finally, the magnetic flux density, which is the total magnetic field lines, is the sum of these two terms, and in CGS system can be expressed as B equals H plus 4 pi m. These three terms should have equal units, but numerically the units are same but named differently as we measure magnetic flux density in Gauss, magnetic flux intensity in Oersted, and 4 pi m in Gauss. To characterize the magnetic behavior of a material, we need to know what is the sign and magnitude of m and also how it varies when we apply an external magnetic field. To explain this, we have two quantities, the susceptibility and permeability. Susceptibility is the ratio of magnetization to the applied field, is a dimensionless volume. Susceptibility is a dimensionless quantity and tells us how easily a material can be magnetized when placed in a magnetic field. And permeability is defined as magnetic flux induction to the applied field. These two quantities can be related from the expression mu equals 1 plus 4 pi chi. Now, if we have a solenoid which has length L, turns N and carries current I, then the magnetic field at the center of this solenoid is equal to Ni divided by L, and from here we get one more unit for magnetic field strength, which is ampere per meter. Also, if we have a loop of wire which has area A and is placed perpendicular to the magnetic field, then the field is changing at a constant rate, then voltage will be induced in a circuit, and we have expression for that directly proportional to area times the rate of change of magnetic flux. The unit for K is volt second per ampere meter, which also equals Henry per meter and is defined as the permeability of free space. This expression for voltage or induced voltage can also be written in terms of rate of change of magnetic flux density, and from this expression we get the unit for magnetic flux density as volt second per meter square. Unit of a line of a magnetic flux has a name Weber, and from here 1 Weber equals 1 volt second, and therefore we have one more unit for magnetic flux density, which is Weber per meter square, also called as Tesla. A magnetic moment can be produced if we flow current I through a loop of area A, then magnetic moment has an unit ampere meter square, and magnetization, which is magnetic moment per unit volume, has a unit ampere per meter. Similarly, this expression in SI units can be written as B equals mu naught times H plus M. We will measure B in Tesla and H and M in ampere per meter. Many times we confuse these quantities and units because in different situations we need to use different names. With this, we completed 2 sections. Now, in the end of the first section, we said that external magnetic field can influence the spin alignment, which forms the basis to categorize the material. And on the basis of its response to an external magnetic field, we have 5 different forms of magnetism as diamagnetism, para, ferro, antiferro, and ferrimagnetism. To start with diamagnetism, the material as a whole has no net magnetic moment, but when such a material is placed in an external magnetic field, then it will induces small current, which produce magnetic moment in the opposite direction to the applied field, and therefore exhibit negative magnetism, also called as diamagnetism. Because this magnetism is only due to the current, therefore the susceptibility we defined is independent of temperature, is a small quantity, and is negative, as shown in the adjoining figure. Next we have paramagnetism. These materials has uncancelled magnetic moment per atom, but due to the thermal agitation and random alignment, a sample as a whole has no magnetic moment in the absence of applied field. When we put this kind of material in an external magnetic field, then moment aligns in the direction of the field, resulting in small magnetization. Examples of paramagnetic materials are salts of transition elements and rare earth elements. To explain paramagnetism, we have two theories. The first is Langevin theory, which led us to the concept of susceptibility and temperature relation. According to this, susceptibility is inversely proportional to temperature. But many paramagnetic materials do not obey this law because Langevin has assumed that there will be no interaction between the molecules or ions of the material, which is not true, and this limitation is corrected by Wies by the introduction of term theta, which is the measure of the strength of interaction between the molecules or ions of the system. Theta mathematically equals gamma rho times C, where gamma is molecular field constant. Next, we have the quantum theory to explain paramagnetism, which tells us that the spin contribution is twice as compared to the orbital contributions. These two mathematical expressions for magnetic moment due to orbital and a spin motion can be combined using spectroscopic splitting factor denoted by G. Now, when we want to calculate the magnetic moment of an atom in a solid, then we include some assumption. One important assumption is there is no contribution or very small contribution of orbital magnetic moments. This is defined as the quenching of orbital moment. This is due to the effect of crystalline field which is produced by the surrounding atoms on the considered atom. Due to this crystalline field, the orbits are coupled strongly to the crystal lattice and cannot move freely when we apply an external magnetic field. Next, we have ferromagnetism. These materials have some uncancelled magnetic moment, and when external magnetic field is applied, even at this small magnitude, they exhibit strong magnetism. To explain ferromagnetism, Wies has proposed two postulates. First is of spontaneous magnetization, that in the absence of applied magnetic field, there will be an internal field which is defined as molecular field. It will be so strong that it can magnetize the substance to saturation. But if all the materials show spontaneous magnetization, then how we get a specimen which has no magnetic effects? This can be explained using second postulates of division into domain, that in demagnetized state the material is divided into small regions called domain. Each domain is spontaneously magnetized to the saturation value, but the different domains has their alignment in such a way that they cancel each other's effect and exhibit no net magnetization. The process of magnetization then can be explained as conversion of multi-domain state to a single domain state in which all the domains are magnetized in the direction of the applied field. The adjoining figure has a relation between specific magnetization and temperature. The temperature Tc at which susceptibility has infinite value is the same at which spontaneous magnetization occurs and is defined as critical temperature or Curie temperature. In ferromagnetic materials, the physical origin of the molecular field is the quantum mechanical exchange force, which depends on the relative orientation of the spins of the electron. The expression for energy can be expressed in terms of particular integral Jx, and its magnitude will decide that we are going to have ferromagnetic material or antiferromagnetic material. For positive values of Jx, energy of the system will be minimum when spins are parallel. and this is the basics behind the ferromagnetism. Because this exchange force depend on the interatomic distance and not on geometrical regularity of atom position, therefore for ferromagnetism we do not need crystalline material. To explain ferromagnetism, we have two theories, localized moment theory and band theory. LMT assumes that electron is attached to particular atom and magnetic moment is localized, but cannot explain non-integral value of the observed moment per atom. But band theory assumes that electron belongs to the crystal as a whole and can move freely inside the crystal to have partial contribution for the magnetic moment, and therefore in this way it can explain the non-integral value of observed moment per atom. Next we have antiferromagnetism, which uses two concepts we discussed earlier. The first is localized moment theory, that electron is localized to certain atom, and second is that here the exchange force, the Jx value is negative. Therefore, we get the minimum values of energy when spins are anti-parallel. Neil has explained that molecular field in antiferromagnetic material is such that if there is any tendency of particular ionic moment to point in one direction, then that will be immediately counteracted by a tendency for the moment on an adjacent ion to point in the opposite direction. It can also be explained that there are two identical sublattices of magnetic ions. Each of them is spontaneously magnetized to saturation, but in zero applied field they have opposite directions and therefore cancelled each other magnetization effects. When we apply magnetic field in either parallel direction or in perpendicular direction, we will have magnetization in the direction of field in case of antiferromagnetic materials. Therefore, the susceptibility of the system is small and positive at all temperature. The temperature Tn at which susceptibility is maximum and after this susceptibility decreases is defined as the Neal's temperature for antiferromagnetic materials. In real system, we observed that parallel or anti-parallel alignment is not specifically meet, as they can be slightly tilted or canted out of alignment. In antiferromagnetic material, as we discussed, that it will also have exchange interaction, and here this will take place by the mechanism of indirect exchange, which is also called as super exchange. This can be explained through the example of Mn2 and oxygen ions. Here, if two Mn plus 2 ions being brought up to an oxygen ion from a large distance, then initially they have no related effects and they both are independent to the oxygen's presence, as oxygen has no net magnetic moment. But when a manganese ion with upspin is brought close to the oxygen ion, then the upspin part of the oxygen ion will be displaced because parallel spins repel one another. If now another manganese ion is brought up from the right, it is forced to have a down spin, and this strength of antiparallel coupling between metal ions depends on the bond angle AOB. Last, we have ferrimagnetic materials which show spontaneous magnetization at room temperature, and similar to ferromagnets show domains have saturation effect and hysteresis effect. Above Curie temperature, they will convert them and become paramagnetics. The most important ferrimagnetic substance are certain double oxides of iron and another metal, which are called ferrites. Often we confuse that with ferrimagnetism and ferromagnetism. This can be explained by taking the example of nickel ferrite. There is one nickel ion which has moment of 2 Bohr's magneton and 2 iron ions each with a moment of 5 Bohr's magneton. If nickel ferrite is ferromagnetic material, then there will be positive exchange force which produce parallel alignment of all these moments, and the resultant moment per formula unit would be 12. But we observed experimentally that the magnetic moment of nickel ferrite comes out to be 2.3 Bohr's magneton. This marked difference shows that the ionic moments cannot be aligned parallel to one another, and nickel ferrite is not ferromagnetic but ferrimagnetic. Similarly, we often confuse ferrimagnetic materials with antiferromagnetism, because here also ferrite crystals occupied two different kinds of position, which we called A and B sites. Also, Neal made the basic assumption that as an antiferromagnetic material, in ferrimagnetic materials also the exchange force acting between the sites will be negative. But the two sublattices have different magnitudes, therefore they do not cancel each other completely, and we have net spontaneous magnetization. Thus, we can conclude that ferrimagnetism is an imperfect or incomplete antiferromagnetism. Now, the last section of this discussion is ferrites crystal structure. Ferrites are one of the most important ferrimagnetic material because of its wide applications, which range from wastewater treatment to high frequency magnetic devices and biomedical hyperthermia. To understand their magnetic behavior, we must examine their crystal structure in detail. The magnetic ferrites fall mainly into two groups on the basis of their crystal structures. First is cubic and second is hexagonal. Cubic spinel ferrites have general formula MoFe2O3, as we discussed that ferrimagnetic materials are double oxides of iron and another metal. Here M is divalent metal ion like manganese, nickel, iron, cobalt or magnesium. It has spinel structure with one formula unit AB2O4. Here A and B are cations and oxygen is an anion. The arrangement we will discuss later, that it can have normal and inverse structures. Now, to explain the structure of ferrite, first we recall some basics, that in this one formula unit AB2O4, oxygen will provide the structure and space for metal ions to occupy the interstitial sites between them. Oxygen will form the closed pack cubic structure. In a cube, for FCC arrangement, 8 atoms will be present at the corners. Because each corner is shared between 8 cubes, therefore it has a contribution of 1/8. Therefore, the total contribution through this corner atom in a unit cell will be 1. Similarly, FCC will have 6 face-centered atoms, each shared between 2 cubes, and therefore has a contribution of 1/2, resulting the total contribution from face-centered atom is 3. Thus, in an FCC unit cell, there will be 4 oxygen atoms. Now, these metal ions A and B will occupy the tetrahedral and octahedral voids in the FCC structure. First, we understand where are these tetrahedral and octahedral voids are present. So, for tetrahedral void, if there are 3 atoms which forms this triangular shape and one atom is present above it, then it will form the tetrahedral geometry, and the space which is present between them is defined as the tetrahedral void. Similarly, if there are 6 atoms, 3 each forms triangular base opposite to each other, then there will be a void in between them, which is the octahedral void. In a cube, we can understand that where these tetrahedral voids are formed. So, if we have the FCC structure and we consider these 3 face center atom which forms the triangular base, then with the corner atom we will have one tetrahedral void at the body diagonal. Similarly, we will have one more tetrahedral void opposite to this body diagonal. Thus, we can say that In a body diagonal, we will going to have 2 tetrahedral voids. In a cube, we have 4 such body diagonals, and therefore total number of void in an FCC structure, a tetrahedral void, will be 8, twice the number of atoms FCC crystal has. For octahedral void, it can also be understood as if there are 4 atoms which forms the planar base, and 2 atoms above and below it provide the octahedral geometry. In a cube, this octahedral void can be found at the edge center, where these 4 atoms forms the planar base and 2 face center atom provide this octahedral geometry, and we have the octahedral void at the edge center position. One more octahedral void is present in a FCC structure, and that is at the center. In this way, we can say that there will be 12 edge centers atom, 12 edge centers octahedral void in a ferrite, each with a contribution of 1/4. So total contribution through edge center void in a unit cell will be 3, and 1 complete contribution due to the void present at the center. Therefore, we have 4 octahedral voids in an FCC structure. Till now, we can conclude that if we have a FCC unit cell, it will have 4 oxygen atoms, 8 tetrahedral voids, and 4 octahedral voids. Now coming back to our structure, which has formula unit AB2O4, in a spinel structure there will be 8 such units which has 32 oxygen ions. This is the Vesta image of zinc ferrite, which has normal arrangement of atom. Normal means zinc, which is a divalent ion, will occupy all the tetrahedral sites, and iron, which is trivalent ion, will occupy the octahedral sites. Even when we discussed that what is the prerequisite to understand this crystal structure, it is still very complex to understand this because of the partial contributions of atom. This can be explained via tetrahedral sites. As we discussed that if one formula unit has this formula AB2O4, that is 1 A atom will be present. There will be 8 such formula unit in a spinel structure, so there should be only 8 A atoms. But if we look at the Vesta software image, then there will be these 4 atoms which has contribution of only 1, then these 4 have the contribution 1, and these 4 has contribution 1. So there will be 12 atoms present in a cell which has contribution 3, and 5 atoms will be present completely inside the cell. So we have 17 A atom which has contribution of 8. Similarly, for B atom, we have 16 B atoms in the spinel unit cell, and all of them are completely present inside the cell. So finally, we can conclude this structure that the formula unit is AB2O4. We need 8 such units for spinel structure, but in the Vesta software image, we have 17 zinc atom in which 12 are present at edge center, 5 completely inside the cell, making the total contribution of zinc atom 8. 16 iron atoms are present for the 16 iron atoms contribution, and there will be 93 oxygen atoms are present, 60 at the edge center position, 26 at the face center positions, and 4 completely inside the cell, and this way we are going to have 32 oxygen atoms of the spinel structure. The conclusion of this discussion is that magnetism originates due to the spinning and orbital motion of electron. The collective alignment of magnetic moment will determine what will be the material behavior. This is the exchange interaction which actually govern the ordering, domains, and phase transitions. Distinct forms of magnetism arise from different spin configurations. Ferrites are the example that crystal structure controls magnetic properties, and magnetic principles shape modern technologies from electronics to data storage. Finally, magnetism elegantly connects quantum physics with real-world applications. These are the references I used. Also, I acknowledge my supervisor, Professor Naresh Kumar, for giving me this opportunity to present myself in this course. MNIT Allahabad and Ministry of Education and also GIAN course for giving us this academic opportunity to present ourselves in such an academic enriching environment. I also thank all participants for their kind attention. Thank you. So, okay, एक minute. As I said that there will be two types of arrangement. One is normal and the second one will be inverse. The tetrahedral and octahedral voids, what they actually do, that if there is a magnetic moment which is present at tetrahedral void, then due to antiferromagnetic behavior, the octahedral void spin alignment will be opposite to this. So if we have zinc atom at tetrahedral position and iron atoms in octahedral, then all the iron atoms which are present in the crystal will going to contribute for magnetic moment. Because zinc has no magnetic moment, no atom is present to cancel out these magnetism due to iron atom. But if we have any other material which has magnetic moment, for example copper, and it will present at the tetrahedral position, then all the resultant of the tetrahedral position will be cancelled by the octahedral position and we are going to have less magnetic behavior.